Okay, let's get started. Welcome to this morning's talk. Our talk is by Dr. Salman Asif. Yeah, he's from EE of EE Department of University of California, Riverside. His research areas include machine learning, signal processing, and computer vision. Currently, from the website, we are focusing on developing efficient and robust algorithms for imaging and information recovery. And he also published extensively in the related field. Yeah. So today he will give us a talk on lensless imaging. So let's welcome.
All right. Thank you. Thank you for the kind introduction and invitation. Happy to be here and enjoying the conference so far. Really appreciate it. So today, what I plan to do is talk about some of kind of recent and not so recent work that we did on lensless imaging, and give you an overview. Talk about what are some opportunities and some outstanding challenges in lensless imaging. Before starting on the lensless imaging is an example of computational imaging. That's a sub area I work on. Before talking about computational imaging, I just want to motivate I'm sure all of you are familiar with the classical imaging system or cameras that we use. The main goal for almost all these cameras is to map real world scene onto a digital sensor. And centuries of work has gone into improving all aspects of cameras, from lenses to sensing and processing that you do after you acquire the images. Almost sorry, not almost all, but the majority of cameras that we at least use for photography, they are mapped to or designed to give you nearly one-to-one mapping. That whatever we see in the world, that should be mapped on the sensor as accurately and as precisely as possible. So in terms of spatial resolution, in terms of color and content, and then usually we do some post-processing after that to do some enhancement, to do understanding, to do different kind of processing. And in that sense, the boundary between conventional imaging and computational imaging is a bit blurry. But the kind of computational imaging I usually deal with is this setup where the real scene is mapped onto the sensor as some coded measurements. So you're not getting an image of the world. So here is an example that X is, say, your scene in the real world, and then there is some sort of propagation that is happening, and then in this example I'm showing a coded mask that is placed in front of the sensor, and the recorded measurements on the sensor look like this this pattern you see in the middle. And the task for computational imaging in this context is that we want to recover the underlying image X from the measurements Y that we are recording on the sensor, and we can sort of model this measurement process or the forward process as this operation phi that is applied to X, and we have to solve this inverse problem to reconstruct the image X from the measurements. And this phi depends on different it depends on different parts of this design. So how the maybe optics and different masks or other propagation that is happening in the acquisition process, that determines what the phi is for a specific system. And like I said, image recovery involves solving some inverse problem. In order to solve this inverse problem, we usually exploit some low dimensional structures in the images or visual data. So here I'm representing that as this this representation function G, such that a natural image, for instance, can be represented as a transformation of G operator on some latent space vector Z. Okay, so that is really the prior or regularization that we apply when we are solving these inverse problems generally. And the other thing that is happening popular nowadays in that context, earlier, decade ago or so, it was all sort of structured, handcrafted models or priors for images or visual data, like sparse, low dimensional, low rank representation. Nowadays, a lot of that is done by a neural network. So you train a neural network that is trained to represent natural images or the kind of images that you're interested in. It can be other domains as well. Anyways, so this is a very high level and general representation of the kind of inverse problem that we solve. The first term really involves some kind of measurement loss. You want your reconstructed signal to match the observation that you're making on the sensor. So some loss, measurement loss between the observation y and then your simulated measurement that you would get for the underlying x. And then regularization here is, like I said, it can impose different priors on the signal, that what your image that you're trying to, or signal that you're trying to recover should belong to some manifold or representation that you have either learned or you have hard-coded in the system. So that is a very high level pipeline for many of the computational imaging systems that we work on. The lensless imaging that I will talk about, that is a specific example of computational imaging in which we get rid of the lenses in our cameras. And the motivation for that is we want to relax some constraints on cost, weight, shape, sizes of the cameras, and that comes at the expense of computation, because now you're not able to get a sharp or a focused image of the world. You're getting some coded measurements, and then you have to solve an inverse problem to reconstruct what was the underlying image. In this talk, I will talk about, like I said, overview of lensless imaging. So basic image formation and reconstruction model, and then talk about some of the work we did for 3D reconstruction or depth recovery with these measurements, either with a single code or with multiple coding, and then talk about some of the enhancements that we have done, and I'll conclude with some application and ongoing challenges that we see in this space. So main motivation for removing lenses or building some lensless cameras are, there are few of them I've just listed here. You want to seek some small lightweight design. So lenses, especially if your sensor area is big, lenses are big, so you want to potentially get rid of that. When we are using these conventional lens-based systems, their thickness is proportional to the width of the sensor, so they are quite bulky and big. If you want to make a flat camera that is really large area, then you cannot afford to put a lens on it, so you have to do some other imaging. And then other motivation for us that when we started working on it was that, can we build these flexible or curved cameras, because electronics sensors are getting there. So if you want to use those flexible or electronic image sensors, you cannot put a standard or conventional lens. So can we put some other material, coat it on top of the sensors and image with that? And potential applications can be in the wearable space, or endoscopy is a potential application, or some of my colleagues at Rice, or in other places, they put these really lightweight sensors on the mouse brain and do some imaging, live imaging, or you can miniaturize and put these things in some other devices where weight or size is a real constraint. So that is the main motivation. Like I said, here's a high-level illustration of how a lens-based system works. So this one is on the left-hand side. It is representing a point source. So light goes from that point source towards your aperture. We have a lens there, and lens is a focusing element placed at a certain distance that depends on the focal length, maybe. And then a single point source is mapped to a single point on the sensor if you are imaging it correctly. And if you think about it from the point split function representation, then you're getting a very sharp and localized point split function, kind of a Dirac impulse. And that is the PSF that is convolved with your image, which means that you're getting one-to-one mapping of your single plane in the scene onto the sensor. Okay. If we remove the lens with some other layer here, this module is representing some optical mask. It can be a phase mask which has some different thickness of the glass, or it can be an amplitude mask which is blocking or letting some light pass through, that then determines your point spread function of the system. So if a single point source is shown on is present in the scene, then that point source will give you a certain response on the sensor. And if you have multiple point sources, then all of them will give their own response on the sensor, and we are recording their superposition on the sensor. And that part we have to undo. Here in the bottom, I'm showing some of the point spread functions that we see in different versions of this lensless imaging system. So flat cam is using this amplitude mask. Diffuser cam is just putting, let's say, some kind of a scotch tape on top of the separating glass, and then flat cam is some other designed defective element that gives this kind of a point spread or response on the sensor. Okay, so that is what the kind of lensless imaging I'll talk about. Flat cam is something that I worked on at Rice around 2015-16, and the paper was published cited there. So flat cam, the idea was to have a bare sensor with a fixed binary mask, and the goal for us was to make it thin sort of sensor. So we just a thin camera. So we sort of designed this maximum length sequence pattern, and we just put that in the binary pattern that is sort of amplitude mask. We place it in front of the sensor. So this black rectangle is representing the sensor. This patterned part is representing the mask. We have some scene in front of the in the real world. That measurement I showed earlier, and in this slide, that is representing the sensor measurement that we observe, and then we solve a computational reconstruction algorithm to reconstruct this image, which resembles what we have in the real world, but it is not as close to what we get with a lens-based system. So there is some something that you give to make when you're making this system really thin. So there is some loss in performance or in resolution that we get. But that's the high level or one reconstruction pipeline. Coded masks, or the kind of masks that I talked about, they are not. I mean, we are not the first one to use. They have been used since 70s, mostly for high energy imaging, where you don't have any lenses, any focusing element. So like gamma ray imaging or X-ray imaging, where there is no lens that can bend the light or focus it onto a plane. So those are the standard applications where a lot of these masks and technologies were developed for coded aperture imaging, but they're, like, I guess, standard goal is not to make things thin. It is just to image what is coming. In our in the lensless imaging scenario for optical and visible sort of spectrum, the goal is to make things thin or some other form factor that conventional lenses cannot provide. So that is the main difference. All right. So some more details about the imaging model, just to build the stage for other things I will discuss. So how we can make an image, or what kind of image we see. The animation is not working, sorry, it happens all the time. So what you should have seen is, as I'm moving this point source, the mask shadow on the sensor is moving. So that is what you can also see here. Like, I don't know if you can see my shadow behind it. There's a point source, and then if there's a mask, and if that point source moves, then that shadow will shift. So that is the imaging principle, that every point source in the scene provides some unique shadow at the sensor, and sensor records this linear combination of all the sort of point sources in the scene, or response of those point sources on the sensor, and we can just model this measurement process as a linear system and solve an inverse problem to undo that mixing. That is what happened in the background. Some examples again from 2016-17, so things have improved quite a bit since then. But here on the left hand side, you see some static scenes that are there that we've just placed in front of that prototype I showed earlier. and then on the right hand side it's like you can just capture measurements of a moving object and then reconstruct that from the by solving some inverse problem frame by frame, or you can put some other video priors as well that we didn't do in this work, but later on follow-up works have done that as well. Okay, so that is, in all these examples, the scene is considered plane that is placed at a certain distance, and we are modeling the measurement of the scene onto the sensor. Now, in the real world, if scene has some depth, then we can also reconstruct the depth from the single measurement, for instance. And that is what I'm trying to highlight here, that if you think about point source moving left to right in a single plane, then the point spread function will shift as a function of your point source location. If the point source is moving towards or away from the sensor, then your, I think the animation was working earlier, but now it is on. So yeah, if it is moving away, then your point spread function will shrink. If it is moving towards your sensor or mass, then the point source point spread function will expand. That scaling of your point spread function is a function of your depth. So in other words, every point in the 3D scene also casts its unique, or yeah, let's say unique, it's a strong word, but its shadow on the sensor, and sensor is recording a linear combination of the entire 3D scene. So in that sense, it is a highly underdetermined system in many cases, where you are capturing measurements of the entire 3D volume onto a single sensor. And we can model the mapping of the scene or surface onto the sensor as a linear system in 2D only if the depth is known. If the depth is not known to us, then it is what I call it's a feature and a necessity as well. That if you do not know the depth and you assume a certain depth and you represent your linear system, then if the depth, there's a mismatch in the depth, then your reconstruction will suffer. So that is what I mean by that being a feature and a necessity. Yeah. Any questions so far on this? Okay, so I can move on. So we and other groups as well, they this part, by the way, this is also not new. Again, if you go to coded aperture literature, 70s, you will see the same observation made in coded aperture imaging as well, that depth is encoded in those systems as well. Anyway, so we started working on, but at that time it was not like these prior based reconstruction was not well known. So nowadays we have those tools available. So things are, we can do better reconstruction probably than we could do it like 40 or 50 years ago. Anyway, so we can perform single image based 3D recovery. What we usually do, we and other groups as well, that we solve some kind of a sparse recovery problem on a large 3D volume. So there are some priors that we can assume. For instance, this diffuser cam or 3D version of that, they assume a sparse representation of the scene, that the scene that we're observing is sparse, like microscopy scene, where the voxel, if you divide your scene into different voxels, then it is not occupying the entire volume. Only a small subset of the volume is occupied. So you can put a sparse prior on the entire volume and reconstruct it, or you can do some other structured prior and reconstruct it. We did some work on solving this problem by basically solving a non-convex problem, where we want to jointly estimate the depth of the scene and the intensity of every point in the scene, and that is an underdetermined and non-convex problem. I will not go into the details of this, but I'm just showing it to highlight how we model this. So here, each point on the sensor, this blue line is representing the sensor, and then there is a light source, for instance, that we just discretize the scene in the angular space, and then the model that we assume is that in a particular angle, that scene is at a certain depth. So it's a surface that we want to reconstruct from the lensless measurements that we are acquiring, and if we represent the system in that manner, then every sensor pixel can be represented as this projection of the scene that is discretized in the angular and inverse depth space with the corresponding mask, depth dependent mask that we get based on the mask pattern, or the PS depth dependent PSF that we get based on the mask pattern. If the depths of the system are known, then this is a linear system. If depth is unknown, then it is a non-linear system where we have to jointly estimate over the depth and the intensity of the scene. So that is what we solve. Some yes. So it is like a light field. Yeah, yeah. So, I think with the light field, you get that. So, so you are capturing the light field. You just don't have a lens there. So the projections you get. What's it? Yes, integration. But if you, so, I know exactly what I think I know what you're talking about. So with your light field diagrams, there is an integration that happens, but here we do not get that rotation of 90 degree. If we represent this as a light field, we do not get the that 90 degree rotation in the two planes because there is no lens involved here. Mm-hmm. Yes. 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 Something like that, but it is not the reconstruction is still non-linear. You do not get a linear system out of it. Yeah. We looked at it. It does not help us in solving the problem easily. Yes. Yeah. But I'll be happy to talk more on that later. Um, anyway, so the way we solved it using a two-step process where we first we discretize the scene into some finite number of depth planes. We solve a greedy algorithm to get a coarse estimation, and then we solve a non-linear joint depth and scene reconstruction problem using that coarse depth map or depth planes as an initialization, and that gave us good results in simulation. So I'm just showing it here. One thing I maybe skipped over, these lens-based systems or lensless systems, when we are taking measurements, you can imagine it's a small sensor, there is a mask in front of it. You cannot get the same kind of 3D reconstruction that a depth camera gives you. You get a depth dependent effect on a very small range. So that is one thing to note here. So here the range of depth is like within a like 1 to 4 meter, for instance here, or 3 to 10 meter. That is in simulation. And main thing I wanted to highlight is like if you change the uh, the the sensor area, the pixel sizes or area, then that has an effect on that gives a different quality of depth reconstruction. Um, anyways, I'll go to the main result or prototype that we built. So here again we built this sensor that has 512 by 512 sort of array. We used a sensor to mass distance of 4 millimeter, which is large for the lensless cameras, but in order to get good depth reconstruction, depth resolution, we have to give it a certain depth, so that certain thickness, so that we can do good depth reconstruction. And physical size of each feature is this number. Just wanted to show some examples. So if we take this kind of a scene, so here the depth range is maybe less than a meter, half a meter. So that is the kind of scenes that we can where we can do good depth reconstruction. So that is what I'm showing here. It's a slanted plane. If you just use greedy method, you do not that is kind of our initialization. You do not get good reconstruction. If we do 3D discretization of the scene and then impose some sparse prior, you are getting some artifacts. But if we solve that non-convex or nonlinear optimization problem, then you can make at least some texture in the world, in the scene, and then some decent depth map from it. Like I said earlier, the problem is not always depth estimation. It is just that if you do not have correct depth map, you will not be able to reconstruct the image either. So that is those are some examples. Okay, next one. So what I showed you, this one, That is the case when we have a single shot and we are trying to do 3D reconstruction. That is a challenging problem. We can simplify that problem quite a bit by capturing multiple shots with even with the lensless camera, but just capturing multiple shots. So we did some work on 3D reconstruction with multiple measurements, and that was a joint work with Ashwin Shankaranarayan at CMU and his student and my student at UCR. And we have these two papers that mainly use multiple sets of measurements, and I'll just explain what that setup looks like. So here's the imaging model, similar to what it was before that. We capture 3D scene using a lensless system. So we can assume that 3D scene is discretized in some number of planes. So that is one type of discretization we can assume. And sensor measurements, like before, it will be just depth-dependent convolution or projections of different planes and their summation onto the sensor. That is what the measurements look like. I have, I think, some picture to further highlight it. So here on the left-hand side, you see a 3D scene. What scene represents is there's a mesh that is part of the scene. It is not our mask, and then there is a duct or some object that is placed at a certain distance. So what this right-hand side illustration is showing is that because this mesh is closer to the mask surface, you're getting its PSF that is slightly bigger. That is depth-dependent effect, and then duct that is at a certain distance. Farther from the mask, you are getting a shrunk version, scale version of the same PSF, and then we are convolving with the duct. So I'm just showing these two depth planes, quote unquote, but you can imagine that in a continuous scene, it's the same process that is happening, that you are getting depth-dependent convolution of your different planes in the scene, and then they are added up to give you one measurement. If we can change the mask pattern, then we can get another shot. So that is what we do in this work, that we can change the mask pattern and we can get another set of snapshot of on the lensless camera. And then if we take a stack of these measurements, then we can potentially do better depth reconstruction. So mathematically, we can represent this process as a big sort of block circulant system, where each row, if you look at the first measurement, so y1 is the first sensor measurement that we're getting one image, that is convolution of, and on the right hand side, I'm just representing it here, the d depth planes of the scene. So the first sensor measurement is a convolution of the mask that is corresponding to the first depth plane convolved with the first depth plane, plus mask that is corresponding to the second depth plane convolved with the second depth plane, and then you are adding them all up. So that this matrix is representing basically same mask pattern, just different scale versions of it. Okay. And the first work that we did, we called it sweep cam. There our motivation was, well, one, can we make this 3D reconstruction well posed, because just doing 3D reconstruction from a single measurement is challenging. So can we make it well posed? And then second thing we wanted to do was, can we focus on a single depth plane like a lens based system can do, where you can just change the focal length and you can focus on one point. And we found a very simple solution for this. And what we do is that we capture multiple sensor measurements by shifting the mask pattern. Same mask pattern that we are just shifting. And we are capturing different set of measurements with that mask pattern. And the reconstruction that we perform is we can recover one depth plane that is focusing on one depth plane in the scene by just performing some shifting, addition, and deconvolution of that stack of measurements that we get. Mathematically, we can go back to that system I showed you, and the process which I just described, and I will illustrate it in a bit as well, is that if you want to reconstruct one depth plane from the measurements, then what we do is we ignore all the other depth planes, and we essentially try to solve this part of the inverse problem only. And if we do some simple linear algebra, it turns out that this process is similar to just take your stack of measurements, shift them according to whatever is the shift imparted on the sensor as you are moving the mask, and then perform one deconvolution. Okay, So let me spend a minute or so explaining this from a simple kind of mask. So the simplest mask we can think of is a pinhole mask, for instance. So here this illustration is showing a pinhole mask that is here in the middle, and then it is representing two planes. One is near plane and one is far plane. And you can see that, okay, if mask is placed at a certain distance, then different planes will give you their image on the sensor. Okay, so the far end is representing the sensor. Now if I change the pinhole, it will impart a different shift on the scene depending on their depth. So plane that is closer will shift more than the plane that is farther. That is just because of the perspective. And if we keep moving the mask pattern, then that is the kind of shift we will see. The plane that is closer will get a larger shift, and the plane that is farther will get a smaller shift. If we want to reconstruct a certain plane, we can just shift this stack of measurements and then add them up or average them. And if we shift it according to the shift that corresponds to the alignment of the near plane, then we will focus on the near object. If we shift it according to the shift for the farther plane, we will get the farther plane in focus, and others will be blurred out. So that is what you will get with a simple pinhole mask. If you replace the mask with some coated mask, yeah.
This involves taking multiple images, right?
Yes.
And so effectively you're capturing a section of the light.
We are.
So then you're refocusing.
Yes. In the pinhole, certain areas just light field. But we can do the same thing with the mask, with an arbitrary mask as well. And the same process, just if you remember the previous illustration, you have a coated mask. We can just shift that coated mask. If we shift it, you will get, again, depth-dependent convolutions of your scene with the mask, different planes in the scene with the mask, and then they are added together. And that on the right hand side, that is the kind of system which I showed you earlier, where the actual measurements are coming from a stack of or multiple depth planes, but we are ignoring. We can sort of choose to ignore some depth plane. We can just focus on one of the depth plane, and that is kind of the equivalent system that comes up. I will not go into the detail, but if you represent the solution of that system, the process is similar to what I showed with the pinhole camera, or pinhole mask, that you shift the measurements corresponding to the plane that you want to focus on. You add them up, and then you apply a deconvolution process here instead of just shifting and adding, because there is a mask that is involved here. So that is what we do in order to get this refocusing or 3D reconstruction effect. Here, like if you shift the measurements using some depth dependent shifts, you are getting this measurement that we're calling focused on the near plane. You apply deconvolution. So you shift, add, that gives you some kind of proxy measurements for the near plane focus, and then if you shift and add in a different way, you get the proxy measurements for the focus on the far field, and that is what the reconstruction looks like. Okay. All right, we have some results on the real prototypes where we are just essentially sweeping through this entire stack or entire depth range, and we can reconstruct from a stack of measurements. We can reconstruct different planes using lensless measurements. Okay, so this scene has, like I said earlier, the range is not very large. It is just like tens of centimeters, depending on the configuration of your mask and sensor. Again, main thing to pay attention is that as you are going through different parts of the scene, the parts corresponding to the correct depth are coming in focus. Obviously, we are capturing a lot of measurements in order to, or stack of measurements in order to get that depth reconstruction. On the left hand side, we are comparing with what you would get with a static mask. Not a fair comparison, but that is what it is. Okay, some just qualitative results. I'll just quickly go through them. If there's any question, please stop me. All right. So sweep cam, that is what I discussed. It captures multiple measurements while shifting the mask patterns. The algorithm is fast because you can just select one plane, do very simple shift addition, deconvolution, and be done with it. But it requires a large number of measurements. So for typical images that I was showing you, we shifted the mask on like 10 by 10 or 15 by 15 grid. So you are getting 100 or so measurements for reconstructing a focal stack of your scene. We can do another simplification on this system, and that comes from again classical convolution theorem, that each of these blocks in this system represent a convolution operator, and we can diagonalize the convolution operator using the Fourier transform. So instead of just reconstructing one plane at a time, we can sort of diagonalize that system, and we can reconstruct the entire stack using a very simple computation. So that is the other sort of follow-up thing we did. We called it kind of Fourier cam, but the main idea is that we can diagonalize that block circulant kind of system into a block diagonal system, and then we can reconstruct all the depth values for every frequency coefficient independently. That is what the system boils down to. And it's pretty fast on a single machine. You can just do this reconstruction almost real time. Not just that, we also can represent this acquisition all the way to reconstruction in a one end-to-end or unified system or differentiable system. And then we can also optimize over the mask patterns that we want to use for optimal depths or 3D reconstruction. So that is the second part that we did in this method, because this inner reconstruction process is pretty simple. We can just backpropagate through it, and we can optimize over the mask pattern as well. So that is what we did in this work. Also added some refinement network at the end. I'll be happy to discuss more on that offline. Main thing to highlight is that, yeah, you start with some initial mask patterns, but then as you train this network, or you don't train the network, you train over the mask parameters, for instance. So if you train over the mask parameters, you get some better mask parameters that gives you better depth reconstruction than the standard or handcrafted or hand selected mask patterns give you. All right, so on the right hand side, it is showing some test example where if you look at some discretized depths scene, 3D scene, and try to reconstruct using the MLS kind of mask pattern that we were using versus learned mask pattern, we get good reconstruction in the depth or 3D space. We built a prototype using programmable mask because in this case mask pattern is changing. So, but that was mainly for experiments. Here I have some results from our prototype, and what you see in all these videos is we are reconstructing a 3D volume, but then for visualization we are showing different depth planes from that volume. So you see when it starts on the top, the depth is increasing. So when you are closest, the depth is small, that depth is relative to the sensor. You see the mesh that is in focus and duct was out of focus, and then as you are sweeping through that through the scene, your duct that is behind that mesh comes in focus and everything else is blurred out. So that is an example of reconstruction that we can get with this system. On the left hand side, I'm showing you for reference the results that we get with sweep cam, where we are ignoring all the depth planes and we are focusing on reconstructing one depth plane at a time. So there you expect some interference, and you're not inverting that actual system that provided you the measurements. You're just approximating that reconstruction using a simple computation. Some more results. So on the left hand side, it's a scene with different toys at different depth planes, and the main thing you will see is that as we are when we can reconstruct this entire 3D volume, basically you are getting very precise depth information from the for different objects that are present in the scene. Some more examples like two cards on the bottom, for instance, when you are closer, when we are just visualizing the plane closer, then that card is in focus, everything else is out of focus, and as you are going back, then the remaining parts come in focus, etc. Here's some comparison of like if you can use separable mask pattern or random mask or the kind of learned mask. The main thing that we observed was that learning helps quite a bit, that you can learn over the mask pattern, and that gives you better reconstruction than just randomly selected masks or shifted version of the MLS patterns give you. The last part of this pipeline was this refinement network. We also observed that it helps in once you have the a coarse or multi-plane reconstruction of the scene using by solving that kind of a linear system. Passing that stack through a refinement network that we call, which takes that stack of measurements and maps it into the texture and depth map that provides some smoothing of the in the reconstruction, and that is what we performed. And results. This is what the results look like. That if we are just using some hand-designed algorithm to reconstruct the depth map of the scene from the stack, from this stack of or volume that we have reconstructed, we get a depth that has multiple holes and inaccuracies. But taking that stack and training a simple unit kind of a network to give you a smooth texture and depth map gives a much better reconstruction. So that is main stuff I had to present for the 3D reconstruction. Then later on, we also tried to combine lensless imaging with some coded illumination. That was motivated by some project where we wanted to do imaging under the display, and we wanted to use the display part to illuminate the scene that we are trying to image. That was kind of our motivation. But at the end, what we did was that we used a projector to illuminate the scene using some coded pattern, that is the structured illumination, and then we imaged that coded illuminated scene using the lensless measurements, and using a small number of these coded illumination based measurements, we can do much better reconstruction than we can get with a uniform illumination. And those who understand the effects of this convolution that lensless or mask-based cameras provide. This illumination helps significantly in the reconstruction because the points that are close to each other in the scene, their point spread function is most correlated. So they are very difficult to reconstruct or resolve. When we are providing some coded illumination pattern, we are essentially isolating the scene into a bunch of separated points, and that reconstruction becomes much easier. And that is what essentially we observed. We played with different kinds of illumination patterns. The simple shifting dot pattern provided near optimal or very as good as reconstruction as possible, or you can have sort of orthogonal patterns like Hadamard or some other patterns, and sweeping through them and capturing a bunch of measurements gives you very good reconstruction compared to what we can get with a single uniform illumination based imaging. Here, this was a setup. I'll be happy to discuss details of it later. In the interest of time, I'll just show some qualitative results. On the left hand side, that is what the real lens-based camera sees. That is the left. If we use conventional lens-based camera with single shot, that second column is showing the measurements. If you are allowed to use some coded illumination on the scene, then we can get that rightmost reconstruction, for instance, or as you're increasing the number of illumination pattern, you can see that the performance or reconstruction quality improves. Other scenes, similar trend, and I don't think I have that result. Now, recently or in last few years, many deep learning based methods have been proposed to enhance the quality of reconstruction. Many of them, like this kind of reconstruction where you have a text there and resolution is not as good from the lensless camera, they will give you a cleaner image. The aesthetic quality of the image will be improved, but they do not recover the information that is lost in many cases. So with coded illumination based system, we are not just getting better or better looking images, we are actually able to make the systems well conditioned as well. And the reason I just explained earlier, that um, you are making the points that are most correlated, or PSF that are correlated, to be to have little effect on each other by this coded illumination. We can also use kind of a compressive sensing setup here, that the sensor that we are given can be really small. So if you are if you see, go from left to right, we are starting with a 512 by 512 sensor and then all the way to 64 by 64 sensor. So that kind of sensor, you are just getting just a single shot, but also on a small number of pixels as well. So there you don't expect to get a good reconstruction, high quality reconstruction, but combining the coded illumination with even that small sensor, we can reconstruct a good quality image from that. Okay, in next maybe 3-4 minutes, I want to also talk about some other instances where lensless cameras have been used, not from my group, but from other colleagues. This is a work from Laura Waller's group, where they do this, utilize this rolling shutter, where they capture different sort of lines on the sensor, and the animation is not working. Sorry, yeah, there. From a single shot, by capturing different one image with rolling shutter, they can reconstruct a video sequence as well. So because then you can represent each line that you're acquiring as some measurement of the scene at a certain instance, and then solve the inverse problem to reconstruct a video from that. Similar, or not similar, but you can make the mask pattern either spectrum dependent, color dependent, or you can use the Bayer pattern or some other spectral sensor with the mask, and then reconstruct the multispectral image as well from a single shot. So those are some of the work that has happened in the space. Beyond visible imaging is also an attractive application for lens-based systems, where for visible light, silicon-based or glass-based plastics lenses, they are cheap. But if you go to like some other thermal or beyond visible domain, then those lenses become really expensive. So a mask-based or designing this coding element that can capture some coded measurements, and then with some post-processing you can reconstruct the underlying image, it is attractive for some of those applications. So here is a paper that tried to do this, use this idea of lensless imaging for long wave infrared imaging. In our first work, FlatCam, we also did some experiments with the SWIR, short wave infrared imaging, and the motivation was the same, that those lenses are really expensive, and if you can get away with the lens in that regime, it's quite helpful. Microscopy, there was quite a bit of interest in using these lensless, very thin, small form factor cameras for microscopy. And there again, the idea is that you can break this connection between the resolution and the field of view. You can image a very large area region, because you're very close to your sample, because because you don't have a lens that really restricts the field of view. Other groups have also tried to make these cameras that are privacy preserving, so that you can take these measurements with the lensless camera. On the measurements directly, you cannot see who is in the room or person, and then either just try to understand what is happening in the scene without revealing the identity of the person, or maybe somewhere in some secure location you have the mask values located, and you can do the reconstruction if needed. And some other potential application, like I said earlier, endoscopy can be a good use case, or some small devices which have real constraints on the thickness or weight, etc., or something variable or embedded versions of the camera that can benefit from this small form factor. Okay, just to summarize, lensless cameras relax constraints imposed by lens-based systems. They are lightweight, thin. They can provide large surface area, field of view, potentially flexible and curved geometries. Depth estimation is a feature and a limitation and a necessity if you are working with lensless imaging system, because of the reasons I explained earlier. If you have a fixed mass based imaging system, then we need to solve some nonlinear inverse problem to estimate the depth. And if you have multiple sort of shots that we can capture, then very simple and fast methods can be used for reconstruction. Coded illumination significantly improves the quality of measurements. It has some other challenges. I will not go into that. Potential future directions and challenges. So I've already discussed some of that. So large area sensing, people are interested in putting that under the display. Embedded devices, wearable, foldable sensors, privacy preserving sensors, where you can in principle co-design this optical sensing and downstream scene understanding or detection tasks. Optical encoding with some lightweight computation is in general a very active area for computational imaging nowadays, not just for lensless imaging, even for other kind of optical elements. With lens imaging systems, you can get 3D and large depth of field imaging, large being subjective here. So those are some potential opportunities. Challenges. They are still far inferior to a lens-based system. That is a fact. The measurements that we get, they are kind of diffused and multiplexed. Sensors have very limited dynamic range, so that is one problem that we have usually with many of these multiplexed imaging systems. Depth range is limited to small distances because it is still dependent on the baseline that you're getting with your small sensor. Ambient light, noise, that is usually a challenge with all these lensless systems. Images that I have shown you, they are captured mostly inside the lab. If you take that setup outdoors, you have other effects that none of us talks about most of the time. We can make them like we can cancel out the background. That kind of processing we can do, but it is still something that we have to handle. Video capture and reconstruction, especially for the case when I talked about for 3D reconstruction, when we want to take a stack of measurements, there we cannot do a dynamic scene because we are taking a stack of measurements. Or if you want to do dynamic 3D reconstruction, then we have to use some other kind of priors in the reconstruction. Other details that are really sort of hidden under the rug are like calibration challenges and generalization reproducibility, especially for deep learning based or learning based system that is really non-trivial. Happy to talk about it more offline. And with that, I'll stop. If you're interested in this stuff from our group, we have code and data sets available on these GitHub repositories. It's not an exhaustive list, but some of the relevant paper that I talked about. And happy to take any answers or questions here, or if you have any questions, feel free to get in touch, and happy to talk more. Thank you for your attention.
Thanks to speaker. Thanks to speaker. So, any questions? Okay, I have a question.
Sure.
I believe if I'm right, the main difficulty for reconstruction the figures image is showing the linear system, right?
It is
so
challenging.
The linear system they are using Lensless imaging, the system must be very ill conditioned.
It is ill conditioned, yes.
So in order to improve the quality, do you try some regularizer there?
Yes. So I don't have all the results here. Like I mentioned earlier, one of them, the refinement network, that is what we used. We did try with some deep learning based regularizers. Sometimes they help. I had actually an example. So this was an example, like if you can take original image. So this is the simulated data. Original image, lensless or least squares reconstruction, that is kind of Wiener filter kind of base method or simple least squares with some regularization. And then we have the least squares with some unit based refinement, and then some least squares where we can fine tune that unit for the specific measurements that we are getting. And then on the last one, I have this end-to-end networks. End-to-end networks are where you give the measurements and the network gives you the reconstruction. That is one popular approach. What do you think will be the results for the simulated data? So it's very good quality. Okay. Prototype, real data. So least squares reconstruction is on the left. That least squares with pre-trained network, that is kind of denoiser, artifact removal network. It gives some blurry reconstruction. We can fine tune that and we can get some refined reconstruction on the right hand side. You usually do not recover any details like here. The image looks less noisy with those deep learning based method, but they do not always reconstruct the correct detail. For this setting, if we pass the real measurements to the end-to-end network, which was giving perfect reconstruction in the simulation, it gives garbage. So when system is not well conditioned, good regularizers help, but just naive training of the network is not always successful. So that has been our finding in many of the cases. And related to generalization, I kind of listed as one of the challenges.
Maybe we can discuss
Sure.
this later. Yeah. So any more questions?
Thank you, Professor. And I have a very simple question. How can you optimize the size or shape of your mask? Can you explain more concretely?
Yes.
Because I saw it is very regular, and I guess that you can optimize the interval or position of some little units on the mask.
So, okay, so in this case, we did some optimization. So if this is a mask pattern, you treat this as an array. So you assume some discretization based on the feature size that your mask will have. And for practical reasons, we cannot have a continuous value. So if it's a continuous valued mask that every pixel is just any value, arbitrary value, then it is not very different from like standard gradient descent based method that you write down this reconstruction as your objective, as your output, which is a function of your mask pattern. Okay, so then it's not in standard like deep learning, your network parameters are the variables that you want to optimize over. For the mask optimization, the mask pattern is the variable that you want to optimize over. So you represent your output reconstruction as a function of your mask patterns, and then you optimize over that by just computing the gradient of your loss function with respect to that mask pattern. So if it is continuous valued, arbitrary, that is what you do. But because we implement these things in some optical devices, so they have to be positive valued. It is also helpful to have them binary valued. So for that reason, there's always some kind of quantization that you do after gradient step, that you optimize over the continuous value, then you do some quantization to make them binary or put some kind of softmax operator to bring them close to, or sigmoid operator to bring them within the range of 0, 1. Yeah.
More questions? If not, the speech is over. Okay, you can. If you have further questions, you can send
Sure.
there. Okay. Okay, let's thank the speaker again.
All right, thank you. Thank you.